Yeah, thank you so much for inviting me to speak. I don't know, what's the most interesting topic in the universe, but I picked one that I like very much and that I know is also well known. So if you've heard about it before, hopefully you won't be disappointed that I'll get to something interesting, the continuum hypothesis. So CH will always stand for the continuum hypothesis, so we don't have to write it all out. And I just have a few I have a definition, I have an alternative definition of the continuum hypothesis, and a few comments about it that I hope are interesting for everyone to hear about if you don't know them already. So first, just what is the definition? What is the statement? There's a lot of ways to say it, so let me pick one out of the air to fix as the official continuum hypothesis. It says there does not exist. Now, should I write larger? It's all right. There does not exist a set which is larger in size than n the natural numbers, and I will define my terms before long. So if anything sounds vague, don't worry, I'm aware. Larger in size than the set of natural numbers, but smaller in size than R, the set of real numbers. Okay? So, of course, whenever you see a statement that begins there does not exist, you can always negate it in your mind. Okay? So if you don't like negative things, you could say that there does exist. And that would be a different hypothesis, the opposite of the continuum hypothesis. And considering one is the same as considering the other. So, of course, larger in size, smaller in size could have multiple meanings. Of course, there are supersets of n that are proper subsets of R. So, in that sense, this is ridiculous. But size refers to bijective size. Refers to the following. Okay, so 3 definitions. We'll say that A is at most the size of B if there's an injection from A to B. Okay, so not that they're somehow contain exactly the same, not that B somehow contains points that A doesn't, but that it essentially contains points that A doesn't, or something like that, that it's essentially larger. That's the or equal, so B doesn't have to contain points that A doesn't yet. We're going to move forward. A equals B in size if there is a bijection from A to B, or vice versa, because it's symmetric. And A is less than B in size. Okay, so this is what I mean by smaller in size. If A is less than or equal to B in size and not equal to B in size. So just referring to the previous 2 bullets. Okay, so this one means not just that B, somehow contains more elements, but essentially more elements. That's what I meant to say. Okay, so another way to phrase CH now is that the same statement over there is just saying there does not exist a set A such that the size of the natural numbers is strictly less than the size of A, and that is strictly less than the size of R. So that's the statement. In order for the statement to make much sense, wow, I don't really have 2 boards here. Do I have the top half of this board, but maybe not the bottom half of this board. Okay. So in order for this statement to make sense, we should know that n is less than r, so that there is at least conceivably room in between. Okay, so that's a classic theorem that I'm sure you might know. So I'm being very space inefficient. For this to make sense, is that readable? Okay, good. We need to know that n is less than r in this sense here. Okay? So clearly n is less than or equal to r because the identity function is an injection from the natural numbers to the real numbers. But could it be actually equal? And it cannot. That's Cantor's first theorem, I guess, or one of Cantor's theorems. Right? Which just says there is no bijection f from n to r. Okay? And many proofs of this, famously called the diagonal argument. That's a familiar way that it was presented. Here's one that I like very much. Assume f is a function from n to r. Okay, so somehow f of n, if we draw the real numbers, somehow f of n is enumerating one at a time every single real number that exists. So here's the analysis proof of this theorem. Suppose that f of 1 is somewhere here, say. Okay, then fix an interval that avoids f of 1. So let's let a1 be a closed, bounded interval of positive length, not containing a1. And now just continue to f of 2, f of 3, and so on, each time shrinking the interval that you had before. So let an be a decreasing sequence of closed, bounded intervals. And now let's of positive length. So not the empty set, for example, and not a single point. Such that f of n is not in an. So in my picture, wherever f of 2 is, I'm just going to shrink a1 a little bit to find a shorter interval that avoids f of 2. So if f of 2 is over here, I'm fine. I don't even need to shrink it. But if f of 2 happened to be inside a1, then I would just shrink it a little bit on the left or right hand side, or both, in such a way that I avoid f of 2. It's very easy to do, right? If you just want to miss one point, you can shrink yourself away from it. Okay, so that way we get a sequence of intervals that looks like this. And it's a theorem and analysis, which could be called different things, the nested interval property or the nested compact sets property, or sometimes it's just a fact about compact sets, that there exists a point in the intersection of all the a n's. Okay, so since an are compact, there exists x in R that is not in any of the ANs, okay? And that could be taken to be just the supremum of the left endpoints of the ANs. So e.g., there might be more than one such x, but there always is at least one sup of left endpoints. Okay. So therefore x is in all of the ANs, so it's not equal to any of the f of n's. Because remember, f of n is not in AN, and x is in AN. Oh, did I do this wrong?
It's just the intersection.
Yeah. X in the intersection of the ANs. What did I do? I did the intersection complement. Sorry. Thanks for your hands. Please shout out any time. X in all of the ANs, as in the picture. Okay, so then x is in AN, f of n is not in AN, then x not equals f of n for all n. So f is not bijective. That's Cantor's theorem. Okay, so what we have is that n is less than r, and the CH is asking if we can stick anything properly between. Other questions at this moment?
We can definitely stick irrationals.
Okay, so we can definitely stick sets inside, but will they have this property? So that's exactly the next thing I want to talk about. So let's, I don't know, preserve this a little bit. But get rid of this. It's hard for me to expose the whole thing at all times. Okay, so CH will be now that statement. It's interesting because most sets that you think of between the naturals and the rational and the reals turn out to be either the same size as n or as r. So CH is interesting because most sets A that are just in between in the usual sense, they contain points, outside of n and inside of r, turn out to be the same size. To be the same size as n or r. So this is kind of a series of exercises, I guess. But if you think about like integers, or as you suggested, the rationals, these contain properly more points than the natural numbers, so I can get rid of this or equal to. Okay? But if you know about a little bit about bijections, it's not hard to think of a bijection between the naturals and, for example, the integers. The integers just contains about double as many points as the naturals, but that doesn't really grow in size. You could identify the odds with the positive numbers and the evens with the negative numbers, for example, and that would be a bijection. And as well, the rational numbers, it's not a huge amount larger than before, and you can even go up to A, the algebraic numbers, so with radicals, okay, and more, with roots of polynomials. With integer coefficients, these are, you probably know the word countable, okay, uncountable, countable. I haven't defined it because I don't need to, but these are all countable sets, so these are all the same as n in size. Okay. On the other hand, if you tried to sort of start with R and whittle it down a little bit, a common set that people look at is the Cantor set. Okay, it's a very thin set of real numbers, but it's a bit bigger than these. So another example, C equals the subset of 0, 1 with digits whose decimal expansion of all 0.x1, x2, dot, 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 where xi is 0 or 1 in whatever base, or sorry, 0 or 2 in ternary. Okay, you can use decimal if you want. It doesn't matter. It'll be the same shape of set. Okay, is very thin. Okay, so it's known C is uncountable. How it's usually called, it means not the same size as n, so larger than n in size. But it's very thin. Okay, it's called nowhere dense, which means it's not dense. Irrational actually is dense, but it's just countable. C is nowhere dense. So it's topologically very thin. It means it's not dense in R or in any open interval of R. And it's also null, or measure 0, which is just a fancy name for probability. 0. Okay? So it's very thin. But it nonetheless turns out to be the same size as R. Okay, so all these sets where we're making n very, very larger, but not too much, don't break away from the size of n. But then if we pop over and make like a set that's kind of thinning down R a little bit by just picking some of the digits of the decimal or ternary expansion, then that doesn't meaningfully cut down the size beneath the size of R. Yeah.
Sorry, I think I'm being a bit dumb here, but
no, you're not.
So these numbers are 0.x1, blah, 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 but each one is just 0, 1, or 2, each of the digits. So I don't understand how you can't count it by just doing like starting from 0.1, 0, 0, 0, then 0.2, 0, 0, 0, then going 0.1,
Excellent question.
1, and then just continuing.
So you're just trying to organize the decimal expansions by the starting, kind of lexicographically or whatever. The thing is, all of your numbers will end in a constant sequence.
Yeah.
So they're eventually repeating. So they're rational.
Okay.
So you're missing the like pi. And yeah. So it's an interesting, thing to think about. And there are ways to visualize it, but it's not a talk about the Cantor set, so I won't go on too much more. But this is what makes CH interesting. It's hard to name a set that that's in between, and it's kind of I won't call it a theorem or a proposition because that would be vague, but it's kind of a statement that any set that's reasonable topologically, so if it's open or closed, or maybe just half open or a union of half open sets or whatever, then it's not going to be a counterexample to CH. Okay, so I'll just call it a statement because I'm being informal, as I will do many times today, but any set of reals that is, air quotes, reasonable topologically, as these all were, will be the same size as n or r, any infinite set. Same size as n or r. Okay, so that's showing that CH is hard to break. Okay, so this is maybe the story of CH, as many analysts think about it. But I want to give the story of CH as many set theorists think about it. Okay, and so we're going to rephrase it as a statement about ordinals and cardinals. So we've talked a little bit about size, which you know another word for size is cardinality. But what is a cardinal number? Okay, that is going to shed a lot of light on CH. Okay, so that's the next section, ordinals and cardinals. And it's a whole thing, but I'll just give kind of the flavor. So, a linear order is a binary relation satisfying, I'll say that. So I'll write it with kind of curly less than, because less than will refer to the actual less than, like if e is less than pi. But this is some other ordering than the usual one, potentially. Okay, so linear order is a binary relation satisfying the axioms, which my students will know I always get wrong. A is not less than itself. If A is less than B and B is less than C, then A is less than C. So irreflexive, transitive, and connected. If A is not equal to B, then A is less than B, or, I'll just say or, B is less. Okay, so it's also called a total order. And it's any kind of ordering of any kind of set or structure that in your mind you can think of makes it lie in a straight line. So to distinguish it from a partial order, which can have tree-like branching, a linear order just organizes things from left to right. Okay, and a linear order is called a well order. A linear order is called a well order if additionally there is no descending sequence that is infinite. There does not exist a sequence an such that an is less than dot a2 a1. Okay, so the natural numbers is, with its usual ordering, is a well order. So I realize now I should probably do some examples. Okay, so e.g. n with less than has no infinite descending sequence. Okay, so that's fine. Can't go down in the natural numbers forever. If you looked at z, that would be a failure because you can go down to the left infinitely. Okay, as well in q with less than, that's a failure. Okay, if you look at the sequence 1 over n for n and n with less than, that is an infinite descending sequence, so that's a failure. But if you turn it around and look at 1 minus 1 over n, That's an increasing sequence. You can't go to the left in that ordering infinitely many times, so that looks good. Okay, in fact, this ordering is isomorphic to this ordering. Okay, because both of them are just starting at a point, in this case at 1, and in this case at 0, and then progressing to the right infinitely many times. Okay, but there are other examples that aren't. We just have 2 examples, and they're really the same example. We have others that aren't the same. For example, you could take 1 minus 1 over n and 2 minus 1 over n for all n. So this has the picture of an infinite thing and then another infinite thing. Okay? You cannot go infinitely to the left in this sequence, even though it has a double infinities many worth of points. So let me just dwell on that for another moment, because I'm seeing that I've gone quite fast. But the 1 over n is just a single sequence taking you up to 1. Wherever you start, sorry, the 1 minus 1 over n. Wherever you start, there are only finitely many points behind you. So if you go to the left from any moment in that sequence, you will eventually run out of room in that sequence. This one here, if you start here, it's the same thing. But what if you start up here? There's now infinitely many points behind you in that sequence, or in that set. Okay? But I still can't do this, because once I progress down to the bottom of the right half, I will land somewhere in the middle of the left half, which has only finitely many points to the left of it. So I will, at some point, if I go in a downward sequence, need to skip over so much that I can never produce an infinite descending. Does that make sense?
If you stop at 1, for example.
So if you start with 1,
If you stop at 1.
if you stop at 1,
Yes.
then there's infinitely more room to go,
Yes.
but you haven't gone there yet. So now take one more step.
But at 1, it will not be considered linear.
So
that
the-
would be a finite sequence if you stop at the last point after. If you stop at
Exactly, yeah, you haven't done it. Like, to be a well order, it means you can't do this. Oh, yeah, and it's got to go on forever. Yeah. So if you stop after just finitely many steps, you haven't done it yet. You have to keep going. You're forced to keep going to get a counter. Thanks. Very important. Okay, so well orders are a really important gadget in set theory because they help us enumerate things. Okay, so let me kind of dwell on them a little bit longer. So this is a little bit informal, but I think it's okay. So the ordinal numbers are a generalization of the natural numbers. Okay, they are equivalence class representatives of the isomorphism of the well orders. Okay, so as we've seen, sometimes different well orders are isomorphic to each other. We want to consider those the same thing. So if 2 well orders are isomorphic, just identify them in your mind. And then what's left after making that identification is called the ordinal numbers. Okay, so a good way to think about ordinal numbers before I give kind of a picture of the ordinal number system is for every ordinal number alpha, if you don't like the official definition, then here's the unofficial definition. For every ordinal alpha, alpha plus 1 is an ordinal number. And for every set of ordinal numbers, S, it has a supremum that's an ordinal number. There is an ordinal number sub S. Okay, so with that, I can give infinitely much more intuition about ordinal numbers by drawing a diagram or two. Okay, so try to leave it up a bit. Okay, so hopefully that's still there. Okay, so the ordinal numbers, we visualize ordinal numbers and their names. As follows. Okay, so the first ordinal is 0, and all the finite ordinals are just the same as all the finite numbers. Okay, so in other words, for any ordinal we can add 1 to it. That's what I said down here, and just like in the natural numbers, and that part is the same. It's the second bullet point that distinguishes ordinal numbers from natural numbers, that when we consider all the finite ordinal numbers together, it has a supremum. And the supremum is given a name. Okay, so all the natural numbers together is called omega, the last letter of the Greek alphabet, making a tangible object out of the infinite. Okay, but now by the first rule again, we can make an ordinal number omega plus 1. And we can keep doing that forever. Okay, until we get to a supremum of everything we've done so far, which we make a name for again. A natural name for that would be omega plus omega. Okay, so after this comes, so imagine this is below that, omega plus omega, which is sometimes abbreviated omega times 2. Okay, and then we can keep going from there as well. So we can make omega times 3, omega times 4, these are just bullet points, and so on. And the natural supremum of everything that's come before would be omega times omega, or omega squared. So what have we seen so far in our examples? We have seen this example, which is the natural numbers now called omega, this example, which is isomorphic to it. So that one will also be called omega. It's not distinguished anymore. Okay? And this one down here is 2 copies of omega in a row. So which object is that in the list?
Is it somehow related to the axiom of choice?
Yep, we'll get there. We will get there, absolutely. You can't have a set theory talk without the maximum choice.
I don't know.
Yeah.
Would Asaf be against that?
Yeah, he would be. Okay. So this example down here corresponds where in the picture?
Omega times 2.
Omega times 2. So it's omega plus another copy of omega added on to its right side. Okay? And so that is omega plus omega, or omega times 2. And we can keep going from there as well, but we'll say more in a minute. Okay, so these ordinal numbers are generalizations of natural numbers that allow you to count past infinity in some sense, or keep counting without thinking about Infinity is a limitation. Okay, so theorem about well orderings. And for those paying attention to which axioms are and aren't used, this uses the axiom of choice. Don't worry about it. It's not. I'm not going to explain too much further for this talk. But every set where am I? Every set A admits a well-ordered curly less than. Okay? So this statement is actually equivalent to the axiom of choice. It's an axiom that we assume. So this means if A admits a well-ordered, it means that we can enumerate its elements from the first one in the well-order up through the steps of the well-order. So that means that we can enumerate the elements of A with indices that are ordinals. That's a curly less than, not an alpha. So this means any A can be enumerated A equals A beta for beta less than alpha for some ordinal alpha. Okay? Any set A is bijective with an ordinal. Okay. Next question. It says for some ordinal alpha, is that ordinal unique? It's not going to be unique. Okay, because if you've enumerated A by some ordinal alpha, you could just rearrange the points in A by perhaps moving some from the start of the enumeration to the back to make it enumerated by an ordinal larger than alpha. For example, if you move 1 point from the start of the enumeration to the back, it doesn't change the start because there's infinitely many points available at the start, but it does change the back by adding 1 to the end. It becomes alpha plus 1. So this alpha is not unique. Okay. There'll be more than one ordinal that can be used to enumerate set A, but there will be a minimal ordinal alpha that can be used to enumerate A. Okay, so definition. I feel like I need some darker color, so I'll switch. The cardinality of A, written absolutes of A, is the minimum, the least alpha, such that, I'm going to phrase this, such that A is enumerated like this with alpha, with index set alpha. Okay, so perhaps I can explain by updating the picture a little bit. So before I do that, at the start of the talk, we used this symbol, absolute value of A, for size, but we only defined when A is less than B, when A is less than or equal to B, and when A is equal to B. We never talked about what the absolute value of A actually is. Okay, and that's sufficient to do analysis for your whole life. So this is the moment when we're actually saying, what is the cardinality of A? This is the definition. It's the least ordinal alpha, such that you can enumerate A with an index set alpha. Okay? And so if we update our picture a little bit to include which ones are cardinalities of sets. Okay? The finite ones are all cardinalities. Okay? And the first infinite one is a cardinality. Anything that's countable has cardinality omega. Now, when we think of cardinalities, we actually call them something else. So I forgot to say this over here because I kind of ran out of space. But Aleph alpha is the alpha cardinal, the alpha ordinal infinite ordinal that is the cardinality of some set. Okay, so with that, we now have a third name for this object, which is Aleph 0. Okay, now if we add 1 to that, is that a cardinality? It is not, because adding one more element to a set doesn't change its bijective class. So anything where you just add, like Hilbert's Hotel, if you've heard about this, you just have a pool of Aleph 0 many objects and you add one more, it still has cardinality Aleph 0. Okay, it's still in bijection with what you started with. And all these steps, just like going from n to z, z, to the rationals, to the algebraic numbers, they don't really properly increase cardinality. So how do we know that cardinality is ever increased? It's from this theorem. Every set A admits a well order and hence has a cardinality. And we know there are uncountable sets by Cantor's theorem that we proved earlier. Okay, so eventually there must arise, after perhaps a long, long, long wait, there must arise a first ordinal that's not in bijection with Aleph 0. And that ordinal is called omega 1, or Aleph 1. Okay, so omega 1, it's stupid that we have two names for the same object. Omega 1 is the name for this ordinal when we think of it as an ordinal. Aleph 1 is the name for the same object when we think of it as a cardinal, but they refer to the same object. Okay, but nothing above it will be ticked. Okay, and then of course you can add 1 to that, and that will not be a cardinal because it's the same cardinality as the one above. And you can add many, many, many things to that. And eventually, after a really huge wait, that's even longer than the wait that we had for omega 1, we will eventually get to an ordinal which is not of cardinality Aleph 1, and that will be called omega 2, or Aleph 2. So this is the picture. The ordinals just keep increasing and increasing and increasing. And every so often, in an extremely rare event, we get an Aleph. Questions?
If I may have a question, which
Sure.
I know the answer to, but might be interesting.
Yeah,
How do we know that there is something else beside Aleph 0 than Aleph 1? How do we know that Aleph 2 actually is somewhere?
Right, this is a good question, right. So we proved that there exists a set, like, we proved that R has cardinality larger than N, but I didn't prove the full Cantor theorem that for any set, there is a set of larger cardinality. You can use its power set, the set of subsets of that set. So any set, so we know that this has there exists a set of larger cardinality. We call it Aleph 1, or the least such Aleph 1. I didn't prove it, but it is true that for any set, there exists a set of larger cardinality. So that's why the Alephs will persist forever in the ordinal chain. So yeah, it's a very good observation of an omission. So, other questions or thoughts? Concerns? Yeah.
It's kind of like adding up the history. Do we necessarily know that like it'll be the next
It
Aleph,
seems stupid,
like
but
one
still.
greater cardinality? Can it like jump Aleph, so to speak?
Yeah, so by definition, alpha is the alpha one. So the alephs enumerate all the cardinalities, just by definition. Okay? Like if there was an earlier one, then we would have called that one alpha one. Does that make sense? But then there are questions about where does alpha one actually appear? Yeah.
And so why are we bothering about introducing omega if it actually continues infinitely? It's the same notation of infinity, right? It's
Why
like-
not use the symbol infinity? That's the question? It's a really good question. Is that the question?
Kinda.
Yeah, like,
It's the same principle, isn't it?
and then down here we're gonna write infinity plus. So in fact, the symbol that you use for omega doesn't matter, right? You just pick your favorite symbol from the list of all possible mathematical symbols, and that's something that can be used here. Omega was chosen by Cantor because it's the last Greek letter. He wanted to avoid the infinity symbol because he wanted to avoid people being scared.
Okay.
But you know and I know that it doesn't matter.
But how do we use omega in the sense of? We haven't
Well, it
really
has a
talked
formal
about
definition, right? It's omega is actually equal to the natural numbers physically, but another way the way I presented it as just the supremum of the ordinals. Yeah.
I understand. So if the continuum hypothesis is true, that means that real numbers are cardinality under 1.
Exactly. So that's the next point that I'm going to make. But that's exactly right. So the continuum hypothesis, which I've surely erased by now, says that there's no sets of intermediate size between n and r. So if r is some aleph, which aleph is it? CH is saying it's got to be this first one because otherwise there'd be one in between. So you do understand.
Is it
And I'll write that. Is aleph 1 known in terms of omega? Like, is there an expression similar to these?
Yeah.
It would be inexpressible, inexpressibly large. So no. Completely, inscrutably, it's defined so indirectly. The least ordinal such that there's no objection, blah, blah, blah. It's terrible. It's a really good question. Yeah. Yeah, so it's this AC theorem that every set admits a well order. So its cardinality is just, we know it's in bijection with some ordinal, and therefore there's a least one, and its cardinality is that least one. Without AC, this becomes false, and what you said becomes false as well, and it's a much richer picture. Yeah.
So the whole thing with like the hierarchy of set power set and the increasing is only with Cantor's proof was purely with the well ordering. Well ordering.
It sounds like you're drifting into foundation, which is only like it's sort of a separate issue. Yeah, but it's most of what you say about alephs is only with choice. Yeah.
My first question is if you want to move on or
Yeah.
I have an okay.
Yeah, I have 10 minutes, right?
Okay.
Is that correct? Or do I need to stop at 5? But yeah.
Just a small thing. You say the n or omega
Yeah.
is so omega. To speak it, omega is the supremum of n.
Yes, so I didn't say it, but to set theorists, this is defined, this like,
Oh,
the
okay.
supremum of n is defined to just be n.
If you remember my
Yeah.
first talk,
Yeah.
those are the
But
Yeah.
I didn't
Yeah.
want to, get too into the nitty gritty that Matosh has done. But
Okay.
yeah, they're like physically
Yeah.
the same, even though you're both right. Or
Right,
both
yeah,
right.
yeah.
Yeah. So is it right that I should end in 10 minutes? Because I think I can do that.
I don't think there's anyone in support after
Maybe a few extra is legal.
Yeah.
Okay.
The police won't, they're not going to bust down the door and you start arresting.
Well, I don't want to make people feel bad or like they have to stay longer than they want. But I just have a few more things to say. So one is what was said already. So because of, so after this discussion, this picture, it means we have the alternative statement So we had CH way at the top, it's erased now, but CH2 maybe, it's completely equivalent to CH, says R has cardinality Aleph1. Okay, so finally we go from kind of an analytical statement of CH to a set theorist's statement of CH. R equals Aleph1. Okay, and again, that's just because it's got to have some Aleph, and if it's some Aleph bigger than Aleph1, then that would leave an intermediate cardinality, okay? And so you could make a set that was of that intermediate cardinality, and it would satisfy the negation of CH. Okay, and just for fun, I have one more. Oh no, I have one more that wasn't just for fun. I have 4 statements, so that's CH2. Okay, so another way to say it, that we need for below, CH3. So if R has cardinality Aleph1, that means that you can enumerate the real numbers using this exact ordinal as the index set, or another way to say the same thing is that R admits a well order isomorphic to omega 1. Okay, so R admits a well ordered precedence relation isomorphic to the ordinal omega 1. Again, omega 1 and Aleph 1 are kind of just 2 ways of saying the same thing, but here I'm thinking of it as a cardinal, here I'm thinking of it as an ordinal index set. So we can well order R in a particular type, particular order type. That's equivalent. And yeah.
Sorry. So is n is like n equals to this 0.
Yeah. So n equals this Aleph 0. This is the letter that is the first Hebrew letter, Aleph.
And this like with n is equals to Aleph 0 and R, then for R equals to Aleph 1.
And R, we know that R is bigger than Aleph 0,
Yeah.
but we don't know if it equals to Aleph 1. If it does, we'd say CH is true. Yeah, exactly. It's some Aleph that's not 0. Is it Aleph 1 or is it something else? So you can notice there's many sub-questions of CH now. Is R Aleph 1? Is R Aleph 2? Is R Aleph 3? And so on. Right, these are all separate questions. Okay, just for fun, a 4th statement of CH. So we know that the cardinality of the power set of the natural numbers is equal to the cardinality of the real numbers. Okay, this is an exercise.
Sorry, what is it? Is it the Cartesian product?
No, it's the set of subsets of n. Okay, so P of n, power set, is a set of subsets of n. And whatever, that's a certain uncountable set. And R is also an uncountable set. And these are the same uncountable cardinality. Okay, so you can find a bijection between the two, or if you like, 2 injections, one each way, and then resolve that into a bijection. Okay, and we know from finite sets, for finite sets, A, of course, the cardinality of P of A is equal to, does anyone know? Or
2
to the power
Of the commonality.
of the cardinality. Yeah, I've heard it many places, right? Okay, so set theorists take this as a notation for infinite sets. So set theorist notation, inspired by the finite set situation, we say 2 to the cardinality of A is by definition equal to the cardinality of the power set of A. Okay, so I just wrote the same thing in the other order and put a colon there, meaning it's a definition, not an equality, not an equation. Okay? So set theorists just, we're lazy. Instead of writing P, we write 2. Okay? But it's the right intuition. And so we can rephrase CH a 4th time as 2 to the aleph naught equals aleph 4, which I think is cute. It's not dreadfully deep or meaningful. Let me make that visible. Right, there's nothing deep going on here, but it just we're getting sort of these short expressions. This one up here for the continuum hypothesis, and this one here that's just pure notation as well. 2 to the aleph naught. It could be any cardinal that's not aleph naught. So the question is it aleph 1? That's CH. Okay, so that's the just for fun. And then I don't want to take too long, but I did promise just some equivalents of CH. I have a list here, but let me just do the first one. Okay, like the kind of why do we care? So there's a story, which we won't really get to the end of, that CH is just that, just a hypothesis, because of course no one has been able to prove, like the Riemann hypothesis, no one has been able to prove CH is true, and no one has been able to prove that CH is false. So that makes sense, why it's called the continuum hypothesis. But there's a further story to that, which is that unlike Riemann or other famous hypotheses, we have proved that no one can prove CH is true, and no one can prove CH is false. So it's a really interesting situation, which kind of means you can take it to be true if you like, or you can take it to be false if you prefer. But we don't recommend doing either, but it should then have interesting consequences, as negation should have interesting consequences. It makes it a nice dividing line. I see there's a question.
I was just going to say, so we have a continuum hypothesis. If we assume that it's false, then 2 to the alpha 1 is not equal to 2 to the alpha 1. Therefore, and presumably 2 to the alpha 0 is not equal to alpha for any ordinal alpha. Then we have a cardinal which isn't of the form aleph alpha. So then could we say that the continuum hypothesis is equivalent to the axiom of choice?
No, so that it has to be aleph by the axiom of choice.
Yeah, no, but I'm saying that
Oh, I
if it's
see.
true, then then we arrive.
Probably not
Yeah, no, it's not.
equivalent, but related
Just
to.
implied.
There's a relationship there.
Okay.
Yeah, I didn't have to think about it.
CH,
That is a good
I
question.
think CH implies choice, but not the other way.
I think CH implies sum of choice. Does that make sense? Like some fragment of choice.
Oh, like
Because you could
multiple
well order
choice or something.
this set, right? But you can't well order our other set.
General CH would imply choice. I think.
Sure. Yeah. Okay. Yeah. So there's more to the story, of course, and I don't know it all. So CH is equivalent to various statements in analysis. Equivalent to, or at least implies in one direction, or is implied by in one direction. Many of these propositions hold true. So it does arise so it's not just a set theorist's toy, it does arise in nature. Due to time, I'll just present one. So this is a Sierpinski. Sierpinski was very interested in, unusual objects, right? It's a name I associate with fractals and stuff. but apparently they're all also interested in, well, an unusual object would be like a counterexample to CH, right? So they're interested in equivalence of CH. So CH is true if, and only if, there exists a decomposition of the plane R2 into two sets, A and A complement, such that all the rows of A are countable. By rows, I mean an intersection with a horizontal line are countable. And all columns of A complement are countable. Okay, so this is my first example of several. It's probably the least the least independent interest, but it's just kind of wild, and it's just purely a statement about kind of covering the real numbers, or in this case, the real plane. So let's just see why that's true briefly, and I'll end it there. So there's two directions, right? If we assume CH is true, okay, then take the real plane. And if you enumerate R in using the ordinal omega 1, then this whole picture is in bijection with a very different picture, one where this is an omega 1 axis, and this is an omega 1 axis. Okay, so in other words, just the x-axis is in bijection with omega 1. The y-axis is in bijection with omega 1. Okay, and if CH is true, right, then the points in this plane correspond to the points in this figure. Okay, and now let A equal the set of pairs xy such that x is less than y in omega 1, in the sense of omega 1. Okay, so that just means take the diagonal and color in the super diagonal and call it A. Okay, so then I guess I need colors, but any row of A is just a horizontal segment here, exclusive of the diagonal. Okay, so it's just an initial segment of omega 1, which is countable, because omega 1 is the first uncountable ordinal. And any column of A complement, right, if you look at just the uncolored bits, a column, this one would be the closed one, of A complement would be just an initial segment inclusive of omega 1, which is also countable. Okay, so that's the whole forward direction. I should write more words, but that's the whole forward direction. So you use the bijection of R with omega 1, and it comes out instantly as just a set of pairs that are binarily related in omega 1. Okay, and then the interesting bit, I guess, is just that the converse holds true as well. So if if such a set exists, right? So assume such an A exists. Okay, so this is a bit more abstract. So there's a set A, and looking at its complement as well, a subset of a plane. So A in R2, R2. I'm not assuming a continuum hypothesis. So R could have a large cardinality in principle. Okay, but assume such an A exists. Pick any aleph 1 many rows of A. So just pick any aleph 1 many. So aleph 1 many rows. So that means, you know, you're kind of looking at possibly overlapping sets there. Okay, so pick any aleph 1 many rows of A. So a row is like, you know, I don't know. I don't want to make notation in the short time that we have. Let X equal the union of these rows. Okay? So in other words, pick aleph 1 many points on the y-axis, look at where A hits that row of the plane. Those green lines will all be countable by hypothesis. Right? Every one of these green lines will be countable. Now project them down onto the x-axis and take the union. You get a subset of the x-axis. Okay? And I claim that's all of R. So if you pick any point on the x-axis, you know, so for any x, for any x, if you look at its column, okay, there's only, what is the second hypothesis? The columns of a complement are countable. So there's only countably many points up here that don't intersect A, right? In this column, there's only countably many points. So this is the column intersected with A, obviously. There's going to be only countably many points outside of A. Since we've got aleph 1 many possibilities that we've colored green, at least one of them must meet. So there must exist a green point, a selected row. Right? We have uncountably many selected. So the column of A at X contains all but countably many points. Countably many points. Okay, that means it must include one of the selected aleph 1 many rows. Okay, which tells you that X is in capital X. So I'm running out of a bit of space, but that tells you that X is in X. Why do we care? Well, X is a union of aleph 1 many sets that are countable. So it's also going to have cardinality aleph 1. And X is equal to all real numbers, because for any X, X is in X. So the conclusion there, which I'll just squeeze into here, so X equals all of R, since X has cardinality aleph 1, I didn't prove it, but a union of aleph 1 many sets of size aleph 0 has to still have size aleph 1. It can't be larger in cardinality. Since X has size aleph 1, we conclude C. Okay, so that's Sierpinski. So this is the first, it's a bit short, I mean, it's very short for, I think, a theorem. But it's just the first of like many statements that are kind of read like this, like sort of silly covering of the plane or R3. with very restrictive properties. Okay, so this is the first in a series of examples that are meant to tell you that CH isn't just a play toy, it has sort of geometric meaning as well. And just, just to sort of say without writing anything, I have other examples where CH is used to produce automorphisms of structures with non-trivial properties, and where without CH, it would be impossible to construct automorphisms with those properties. So, fine. And then my very last part of my talk, I've already discussed a little bit, is about the provability of CH. So I'll just say it again, that no one has proven CH is true, and someone has proven that it's impossible to prove CH is true. And the same for its negation. So this status is called independence, when you have a statement that is known to be neither provable nor disprovable. Then we say it's an independent statement. And we know there exist independent statements from Gödel's incompleteness theorem, which is an abstract statement in philosophy essentially, but really mathematics as well, that says there have to be independent statements. But it's such an abstract statement that it doesn't give you like kind of a nice naturally occurring example. So I think CH is really the first really naturally arising example. It was already a well-known problem before Gödel even came around. It's one of Hilbert's 23 turn-of-the-century problems. So it's a really, really well-known problem. And so it's sort of maybe rightful that it ended up being the first really naturally occurring example of an independent statement. And to me, that's just a very satisfying resolution to something that's a hypothesis, to say, well, good thing you didn't solve it because you couldn't have, we would have had a contradiction if you had done it. So it might be seen as unsatisfying because we haven't solved it, but to me it's actually much, much better. It's put to rest in a way that's really kind of interesting in that you can still retain both sides. Because when you prove a theorem, then its negation is gone. But when you can't prove a theorem, then you still have the statement and its negation. When you have an independence result, that is, you still have the statement and its negation. Okay, cool. Thanks for listening.
Yeah, I think we'll take some questions if anyone has any, unless you have to go.
I'm happy to, entertain for,
This is, it sounds kind of trivial, but basically, like, if you can show that, like, that statement, if something is, like, equivalent to the CH, you basically shown it's unprovable.
Then it's, as well, it's independent, exactly, yeah. Yeah, that's right. And half of that as well. If it follows from CH, then you can't prove it's false. And if CH follows from it, then you can't prove it's true, or if I said that right, etc. Yeah.
I have a couple of questions. I guess I'll start with the first one, which is that we got the natural numbers, which are Aleph null.
Yes.
We don't know what Aleph the reals are.
That's right.
We don't know what they are.
Yep.
And then we got these ordinals that describe these sizes, right, in general.
Like the subscript of the alpha is an ordinal.
Is an ordinal
that tells you how big a cardinal
that tells you how
is.
big,
Yeah.
right? But we know, like, we've played around with the reals and the naturals before. Like, those are things we're very familiar with. So I'm just basically wondering, are there other objects that mathematicians used that weren't, like, they didn't come around because of ordinals, right? That turned out to be not Aleph null, or the same size as the reals?
Yeah, so you're
Like a
asking for
different-
like a
a
natural
different-
example.
Yeah, like, are basically the naturals and the reals the only Aleph something sizes that we normally play around with?
Nearly. Is there an answer?
Functions on the reals. That's kind of.
Yeah, so you can kind of keep going. Like, if you think of reals as functions on the naturals, because their decimal expansion is kind of like a sequence, then you can make as well real indexed, sequence. It would just be functions. So functions from R to R, or even functions from N to R, is the next cardinality up. Like the set of all those functions is the next cardinality in the sense that it's like taking a power set again, or doing
Yeah.
Cantor's theorem again. So again, you would know you get a larger aleph than whatever R was.
Yes.
And it's not, again, the distance
Okay.
would not be known. So each time you kind of take another like layer of like functions of those and functions of those and functions of those.
Okay.
You get another higher cardinality, and all the questions will be unknown, like which aleph is it.
Okay.
Yeah. Yeah, it's confusing. Do you think of not knowing what cardinality R is, or do you think of not knowing what aleph 1 is? Because they're like you can think of it either way. Yeah.
Could we express it like Russell's paradox in a similar way, where we have suppose there exists a set of all sets, then you have, but then if we can set the set of functions from that set to itself, then you would have a set of greater cardinality than the set of all sets.
That sounds reasonable. Yeah, sure. Set of functions and a set of subsets, so both kind of like a 2 to the operation. So
Can we say the infinity is also finite?
the omega thing.
Yeah.
Yeah, I mean, it's definitely not finite, but it's very small anymore, right? Like you usually think of, infinite things as large,
Still
but
possible.
So it's like
Yes.
omega is it's like some relatively infinite.
yeah, exactly. Relative sizes of infinity are distinguished now. Like as a kid, I thought of things being finite or infinite, and before Hilbert, people forbade to speak of the infinite, and only as kind of like the unrealized limit of some finite process. And the computer scientist would probably still think the same way. But yeah, to a set theorist, the infinite exists, it's tangible, it's an object that we consider, and moreover, there are multiple different shades or sizes of infinity. There are infinitely many different infinities, and some are very small, even though they're still big.
I'm not really sure how to phrase this question, but you kind of touched on it in the beginning when you said about. So you said how like basically topological sets in practice they're usually either the size of the reals or
Yeah,
the naturals.
that's
like
right.
In practice, like
Yeah, in
it
practice.
seems to me like if you're doing maths like in practice, it certainly seems as if the continuum hypothesis like seems to be true.
That's right.
As in like it's like, which obviously yes, because due to the continuum hypothesis, you're
Being
never
a
going
problem.
to find
Yeah.
like write a set in
You're not going to
between.
just write down a real concrete thing.
Yeah.
Exactly.
However, like I don't know, it kind of I don't really understand like where it starts to break. Like when you're doing maths, it's quite clear you've got these two different sizes, and there really doesn't seem to be anything absolutely between them.
Yeah.
So where does it like start to like
Yeah.
break? Where you start to not really know? I guess where it starts to break is when you formulate theories to do with ordinals and stuff like that.
Exactly. That's exactly right. So there's kind of a branch of set theory that deals with that question and extensions of complexity of like sets. So, the Borel sets, if you've taken measure theory, are like the class of set. When I said topologically nice, that's kind of what I was thinking of. So the open sets, the closed sets, and then anything that can be derived via countable unions and intersections any number of times from open and closed sets. Those are called Borel sets. They're very nice. They're not super nice, but they're all measurable. They all have something called the Bayer property. So they all have some sort of topological reasonability. And that theorem I was alluding to is saying the Borel sets satisfy the continuum hypothesis in the sense that they're all either countable or cardinality of the reals.
Right.
And then above that
okay.
complexity layer,
Yeah.
that's when it starts to break down. So if you consider the projections, like if you have a Borel subset of the plane and project it to
Oh,
one
brilliant.
variable,
Okay.
then that's another level up. And then if you take a complement of that and project one of those and so on, you keep getting layers and layers of complexity higher. And where it seems to break down is around the
Oh,
second layer.
okay.
And that's where you can define ordinals, right?
Right.
So that's exactly good intuition. That
Oh,
once you can sort of define ordinals, which takes a lot of symbols, right, and like big quantifiers and unbounded searches over the real numbers, which are things that are just completely non-computational. Right, there does not exist a decreasing sequence. It's an unbounded search over sequences, which is just a huge search to do. It's not like effective thing to do. That's where it starts to break down. So if everything you do is effective, meaning like, you could imagine a machine carrying it out, or it's
Yeah.
continuous, or whatever.
Like computable?
Yeah, exactly.
Yeah.
Computable, or the generalization of that to the real numbers, to a continuous situation, you're never gonna care. And that's why mathematicians were able to make it to 1968 without, 1965, without worrying too much about the continuum hypothesis. Whatever, the 60s.
Yeah, 60.
Yeah. No, it's really interesting, the boundary between, where such a counterexample can exist and when it really won't be found.
Well, it's nice to know that there is a
A study.
Yeah, like there is
exactly.
a
There's a
Okay.
moment.
Thank you. Okay.
If you would take an interesting remark, which I think the room might like, kind of where set theory breaks a bit, because we've seen it breaking in this way, there's something not provable. But at the same time, when we look at ordinals, we can, in a way, see order on those, that we can see one ordinal is less than another one, and we from that see that that's a well ordering as well. What would happen if we take the ordinal of that well ordering, the resemblance of that well
So I said, it was being very sketchy when I said, like, if you have a bunch of ordinals, the supremum is also an ordinal, because you can glue them together side by side. But if you take all the ordinals, I was careful to say, if you take a set of ordinals, you take a supremum. If you take all the ordinals, it's supremum. Yeah, exactly. It's not seen by set theory. It's not a set. So there's still, like you say,
an infinitive not.
yeah, and maybe that should be called infinity. And Cantor himself really struggled over the concept of what do you call it, O or whatever, like the union of all the orbitals, and went crazy. Probably not because of that, but for genetic reasons. But if you want to say it, he went crazy because of set theory. But those problems are well understood. They fall a little bit outside classic set theory.
Thank you so much. Can we give you another round of applause?